There are so many dark clouds in modern physics. Let's go back to classic physics of early 1900s and ask classic questions for elemental particles. Maybe it is time to revisit quantum mechanics and theory of general relativity. This is our new direction of physics.
Today we're going to continue our new direction of physics. So this is video 13. We're going to continue our self-interacting field theory. Okay. So from last video, we're starting bring our self-interacting field theory into a tensor format to modify general relativity. We will continue that. In the last video, we rewrite Einstein's equation into self-interacting field theory, okay, because we rewrite it into a tensor format. We're able to separate the geometry part, which causes the acceleration, from the geometry part and the gravitation part. And we bring also the scalar part of the interaction. Hopefully, someday we're solving the self-interaction field theory. We can bring the strong interaction, quantum interaction, and gravitation into the same equation. Okay? We already see from previous video that we are able to put the scalar part of the self-interacting theory into general relativity, and also we've seen that in quantum mechanics. So this video will compare the format of general relativity with electroweak interaction, Maxwell's equations, and Newton's law of gravity, and we rewrite the self-interacting general relativity to replace the older general relativity, to overcome the incompatibility between the quantum mechanics and the general relativity. Okay? Because now quantum mechanics became part of this theory. Okay? So in the last video or so, that the new geodesic equations, which Einstein has, not this part, and also these two are together. We have the geometry part, geometry, okay. Okay. We have the gravitational part, we have the scalar part, okay. Okay. So after we define the difference tensor, we see that this is the part of the scalar part. Okay. So if we go back to, if you know the general relativity, okay, so what we have is in the Schwarzschild solution, we have G00 equals B, okay, or 1 over Gm over RC squared. Okay, we have GTT equals 1 over B. Okay, we have G theta equals R squared, G phi okay, equals R squared sine square theta. Okay, so because last time we showed that we said this term equals 0. Okay, because this is very critical, because otherwise people say, hey, Q, you bring new terms. What about the classical testings? Okay, so we see that this is what we got. It's because this times this, the determinant of G, okay, or square root of that, that's equals R squared times sine theta. Okay, that's a square root of that. But what's interesting in that, because in the Minkowski space, G00 or eta 00 equals 1, okay? Eta TT equals 1, okay? Eta theta equals R squared. Eta phi, that's the Minkowski space, equals that, okay? So that means square root of gamma also equals R squared sine theta, okay? So now, if these two are divided together, that means V equals partial log 1 partial x gamma equals 0. Okay, so because in the Schwarzschild solution, the metric, the determinant of the metric tensor and the determinant of the Minkowski space is the same. Okay, that's why this equals 1. Log 1 equals 0. Okay, so that's why it's 0. So that means we don't need to worry about the classic test of Einstein's general relativity. Okay, now we can bring whatever term like this to our equation. It's not violate because it's 0. We can add it. But in the different cases, this term may not be 0. So, but that's not violate Einstein's general relativity traditional test. Okay, so in order to see what the equation, the field equation or self-interacting tensor field equation, what look like, because we know that's our force. Okay, I write the scalar part into theta lambda lambda. Okay, so that's anything you see they're the same, that means they're compact. That's the scalar part. Okay, all possibility you add together, that's a potential tensor. Okay, we introduce a potential tensor because we have the force field theta lambda mu. Okay, so that's like the F mu nu of Maxwell equation. Okay, so but we can write that into some derivative of partial A mu, partial A nu, okay, or x nu, sorry, minus partial A nu, partial x mu. Okay, so we can write this into a partial g lambda v partial x k eta theta k. We can also write it into a derivative. Okay, so because this is the force field. Okay, so this is why we would like to define a potential tensor which corresponding to the force. Okay, like the A mu over here. So my g theta mu nu, it's like A mu over here. That's a derivative. We're trying to make into that. Okay, but all this component makes very complicated. Okay, but we know that's a force. Okay, if we refer back to the Maxwell equation, the Maxwell-Lagrangian equals F lambda mu. Okay, F lambda mu. Okay, that's the Maxwell-Lagrangian. Okay, so that's a Maxwell-Lagrangian. We would like to write, this is our force field, this is Maxwell force field. We would like to use this force field to do something. Okay, because that's like this kind of terms. But what we have over here, we have all these possible combinations, but we have only one force, which is this. If we do something like that, that's what we want to propose. Okay, let's define a field variable similar to electromagnetism. Okay, but we have an extra index. So this is our scalar. Okay, this is our tensor part. Okay, so my Lagrangian, very similar to Maxwell's. We remember we have Maxwell's lambda mu f. That's the Lagrangian for Maxwell equation. Okay, electromagnetism. Okay, for electromagnetism, let's write that. So what we have is an extra term. That's the field self-interacting, because electromagnetism doesn't have self-interacting term. Now we bring a self-interacting term. Just like our Newton's law, our scalar, remember we have log phi equals delta mu phi phi nu, okay? Okay, something like that. So now this is a force for scalar. Now we redesign something to put our two forces, because in our geodesic equation we have two forces. One is a tensor force, another scalar force. We have two forces, okay? So now we put them together, okay, into one force. That's our force field. We redefine like that. So we have a Lagrangian, supposed to be like that, if we don't do self-interaction. But we need a self-interaction term. That's our potential tensor. If we contract with potential tensor, that's where we have something like that. Okay, what the equation look like? Okay, so this is, if we have the self-interacting general relativity Lagrangian, our field equation like that. Okay, so by the way, this is all tensor. No more of fine connections. It's all differential tensor. Okay, so this is where we have a much simpler equation compared with Einstein's field equation. Einstein's field equation equals r mu nu, okay, minus half g mu nu, and r equals minus 8 pi g, okay, t mu nu, okay. Okay, that's what we're trying to write a similar equation, okay. We can derive the equation, okay. So the first term, this term is a divergent term, but Einstein's has diverging, contracting. If you expand it, it's much more complicated, okay. You have many more terms, and how to say that, the meaning, it's geometry, okay. Einstein said, okay, general relativity create a curvature, okay. But now we don't care whether it's create a curvature. We just define a metric field, just like, remember we have the Maxwell equation. We have F mu nu equals partial A mu partial X nu minus partial A nu partial X mu, okay. So we have that, okay. So that's what we see, that we have this very similar to what we have like that, okay. So the field tensor, the self-interacting, that's the potential tensor, okay. That's where bring us the potential tensor, okay. Okay, that's bring us the self-interaction, okay. So this equation is different from Einstein's field equation because we have a boundary over here. Where Einstein's curvature tensor, it has mixed the derivative field into these two terms, okay. And also Einstein's field has space or geometry part in it. We don't, okay. So they mixed this kind of terms because it needs energy. But our self-interacting theory, we will see that it has energy and the momentum the same as the Lagrangian, okay. We're going to show that. So the second term, that's a self-interacting term. So the next one, if we expand the field equations, we will see that, okay, that's a scalar divergence term, that's a tensor divergence term, times by the potential, okay. Now we see this, we have an extra term, okay. So only difference by one extra term of the scalar self-interacting term. Okay, so but this is the same, but we have this in front of that. That will give us boundary. This term will give us a boundary, okay? Because at the boundary, the potential tensor goes to 0. That will give us the boundary, okay? So because now we have the nonlinear term also in the divergence term, that will be able to maybe bring the strong interaction and gravitation into the same equation. This equals 1 in the weak field limit, okay? So that means in the weak field limit, that goes back to exact, if this goes to delta lambda v, okay, that's where exactly the same, this part will be exactly the same in the weak field limit, will be exactly the same as Einstein's field equation, okay? So this equation, only two terms is different. One is the potential tensor, bring the boundary. One is the self-interacting of the scalar field, okay? Because of this term, we will have 3-dimension, 1-dimension, and 2-dimension trapping, okay? Because this term is very similar to quantum mechanics, okay? So you see, if we erase this, we bring back like a quantum mechanics term, except this ratio now is 3/4 instead of half, okay? So how to solve this? Because now it's a metric field. Whether this is exactly the same as quantum mechanics, we can rewrite the equation of the scalars to make it into like that. If somebody, you go home and play with that, it's, in fact, if we rewrite the equation, we will see this term, okay? So the self-interacting is different from Einstein's field except the boundary and the self-interacting scalar, okay? Okay. We already, in the previous videos, we already showed this term bends the field, okay? So that's what we see. But the Lagrangian term, let's go back to the previous one, okay? So the reason this now is very similar to the Maxwell equation because it's a tensor and also it has the tensor gradient, okay, as the field variable, just like a mu nu over here. How to say that? Because of this tensor format, it's already an energy momentum, okay? Because the Lagrangian, previous Lagrangian, this is, if we take a derivative of partial L, partial G mu nu, it's the same as the energy momentum of lambda mu theta F theta lambda V. That will give us energy, okay, of the field. Okay, so basically we can bring this back. So what's interesting is, I didn't show it over here, if we take this derivative to curve the spacetime, we gave the same equation, okay, the same equation, but this will be a minus sign, okay, minus sign. So that means even though our field equation is right in the flat spacetime, we can also write it in the curved spacetime, just like Einstein's, but it's also the derivative in the curved spacetime, okay? So this equation, you can write it into one spacetime, you can write it into another spacetime, but the field equation doesn't change. So in the weak field limit, the potential tensor equals like that. We recover Einstein's equation except something like that. And we don't need the minus 1/2 G mu nu R. No need. Okay, but our tensor, it's energy momentum in flat spacetime. Energy momentum in flat spacetime. Okay, so what we see over here, okay, we see the new equation. Okay, we see a new equation of the self-interacting field under the curvature tensor plus a self-interacting scalar. But the energy momentum tensor we're defining, we don't need curved spacetime. We're in a flat spacetime. So because in the Einstein's general relativity, it has spacetime in there. That means G mu nu, it's in this energy momentum tensor. Now we don't have, okay? And we don't have this extra term Einstein's field has. The field equation, it's about the same, but we have two difference, okay? So even in the weak field limit, so that means our field causing the field spacetime to curve, okay? But the energy momentum doesn't need from the curved spacetime, okay? So this self-Lagrangian, its field is like that. The conservation energy momentum is guaranteed by the Lagrangian Euler equations, okay? So we make the general relativity equation much simpler, much easier to understand. We have a matter in a flat spacetime, generates some tensor field, okay? It's something like that, okay? Even you add a self-interacting term over here, okay? So what's happening that the energy momentum tensor is in a flat spacetime? Because if we see that the Maxwell equation can also write into a Randall's space-time metric. In the previous video, we talked about that. This can be write into the Randall's metric. But then the energy momentum tensor doesn't need to be in the curved spacetime. This is why I think general relativity it's different from my self-interacting tensor field, okay? Which one is correct need to be tested. So in the next video, we're going to talk about the self-interacting general relativity, okay? Self-interacting and Einstein's potential equations and potential verifications by experiments. These two are different, okay? So what we do, Einstein's field equation has two very famous solutions. It's Robertson-Walker metric and Schwarzschild solutions. We were also, because now we have a field equation, we will also take a solution of these two equations to see what's different, okay? We will see that the Schwarzschild has two solutions, and this one means the universe is closed. Because currently, Einstein's not enough matter to close the universe. But our Robertson-Walker metric will be close to the universe, okay? Because we have a boundary, okay? So, but the Schwarzschild solution will have two solutions, okay? One is the traditional gravitation, one is strong interaction, okay? So this is where it's getting closer to my few videos left, okay? But I hope people start to understand from the self-interacting to the rewrite Einstein's field equation, we see the difference between these two theories, okay? Thank you.